In our last tutorial, we're going to go through how to interpret an output file from a Magma Chamber Simulator run. So you'll remember in our last tutorial, we exported our run results and they're saved as an output file, 7 October E. Now this is in our input and output folder within the MCS folder structure. If we go ahead and open that, you'll notice that it looks quite a bit like the actual input file. And this is intentional. This is an echo of the input file so that you can see everything that you did during that run. Say you want to go back and repeat a run because for some reason or another, maybe the mineral compositions aren't quite matching up, or maybe you didn't get the result you expected, but it was pretty close and you want to try again. Well, this is where you go to find out exactly what happened during your simulation. You can go ahead and just copy all of this information down and you will have an exact duplicate of your run. The only additional information in this tab is here at the top. So in row 1, we have the version of the Magma Chamber Simulator that you did this modeling scenario in. In this case, we ran this model through MCS 09AA. That's our newest version. If you've run this model through a different version, you'll have a different version of the MCS here. The second row is the version of Rhyolite-MELTS that your simulation used. So say you used version 1.0.2 to do a run. Up here in cell B2, you would see Rhyolite-MELTS version 1.0.2. For this run, we used 1.2.0, and that's what's reflected. And this is because different versions of MELTS might have different results. 1.0.2 and 1.2.0 use different water saturation models. You would expect to have slightly different results with the same PT and composition conditions. The next tab is the run summary. This is the most important tab in the output file because it gives you all of the data that occurred during the run. So the first column is column B, MELTS run mode. This tells you what process was taking place during each temperature step. So the first row is actually wall rock prime supra. This is the near solidus conditions that occur during the wall rock prime portion of the MCS run. You don't really need to worry about anything in here. Likewise, row 5 is the magma fine liquidus. That tells you the liquidus temperature of the magma. Everything else below is really where it gets down and dirty with the nitty-gritty details. So if we look below that, in row number 6, we have Magma Equilibrate B. So this is equilibrium crystallization in the magma chamber within one temperature step. So after this temperature step, the solids are removed. And so equilibrium crystallization occurs at each temperature step, and the fractionation occurs after each temperature step, but before the next one. And you'll see here in a magma chamber process that's reflected in, FC. If we come down to row 18, we'll see recharge equilibrate. And this tells us, there's a recharge event going on here. Everything in this line is the condition of the recharge magma at the time of recharge. So what is the temperature of the recharge magma? How much mass is added? Of that recharge magma, how crystalline is it? What is the percent liquid? What is the percent crystallinity? Is there exsolved fluid? The second orange row is magma equilibrate C. So this is the equilibrium crystallization within one temperature step after the recharge has taken place. This is the isenthalpic equilibration here that requires the enthalpy convergence steps, if you remember back to our initial input file tutorial. So the first orange line is the state of the recharge magma at the time of recharge. The second orange line is the isenthalpic calculation, what is the hybrid composition? What is the hybridized temperature of your new hybrid magma? We haven't fractionated anything. It's solely equilibrium crystallization here. And then the fractionation is going to happen after this step. And we go back to magma equilibrate B, fractional crystallization. If you have a simulation, you would see something called wall rock equilibrate. That gives you the state of the wall rock at a given temperature. You would also see wall rock change bulk. That's the extraction of melt from the wall rock at a given temperature. And you would also see magma iso T fractionate B. That's that last isenthalpic equilibrium step, the response of the magma composition to the assimilation of the wall rock partial melt into it. Again, equilibrium crystallization, fractionation of cumulates occurs after that isenthalpic step. So column C here, again, tells you what magma chamber process is occurring. It's fairly self-intuitive. Column D tells you the temperature of the magma at each step. Again, if you have recharge or assimilation, it might not be right with that initial temperature decrement that you set. It could be your new hybridized temperature, for example, that you see here in row 19. Column E is the temperature of the wall rock at each temperature step. Likewise, you might have a different wall rock temperature than before if you have assimilation or recharge. F is the recharge temperature. Again, what is the temperature of the recharge magma at the time recharge is triggered? Column G is the total composite system in grams. Sorry, the total composite system mass in grams. So this is the total mass of the system. The mass of the initial magma is always going to be 100 grams. So you can just subtract 100 grams and then you have the mass of your wall rock. Or if you're recharging or assimilating, or if you're recharging, then you can add in whatever new mass there is. So here, our total mass of the composite system is 1,100 grams. 1,000 grams for the wall rock and 100 grams for the magma. After our first recharge event, we're going to add 50 grams of recharge magma. So the new total composite system mass is 50 grams. Column H is the magma liquid mass. How many, out of that 100 grams or out of that, however many grams your magma subsystem is, what of that is liquid? Column I is the total incremental mass of cumulates removed at each temperature step. So remember that magma equilibrate B, that's your equilibrium crystallization, and then the removal of cumulates or the fractionation occurs after that equilibration. So after the first temperature step, we've removed 0.009 grams of cumulates. After the second one, 1.08 grams of cumulates. After the third step, 1.37 grams of cumulates, and so on and so forth. Column J is the cumulative mass of cumulates removed. That's a mouthful. Basically, we are just keeping a running tally for you so that you don't have to add it all up in Excel later. K is the fluid phase. So this is the mass of any fluids that are removed, fractionated after each temperature step. So fluids would include water, and then if you're running a CO2-enabled version of Rhyolite-MELTS, it would also include CO2. If there is no separate fluid phase, then it'll show a 0. So here before our first recharge event, we don't have any exolved volatiles. So there is no fluid to remove as a cumulate. But after our first recharge event, we start removing fluid. Likewise, column L, again, it's just the cumulative of column K. It's just that running tally, so you don't have to add it up later. Columns M through P are in green, and that's the state of the recharge magma at the time of recharge. So you can see that happens in the first orange row. So here we have 3 different recharge events. Rows 18 and 19 are our first one, 26 and 27 are our second recharge event, rows 37 through 38 are our fourth recharge event. And so at the first recharge event, we are putting in 50 grams of recharge. Out of that 50 grams, 11.66 grams of it is liquid, 38.33 grams of it is solid. So you can actually recharge with something that is partially crystalline here. It doesn't have to be only a liquid. The next few columns, columns Q through V, are the state of the wall rock. So here in column 4, at 1,075 degrees, and I'm using this because I didn't assimilate during this run, at 1,075 degrees, we have 1,000 grams of wall rock. Of that 1,000 grams, 96.42 grams are liquid, 903.5 grams are solid. So it's about 90% solid. We don't have any exhaled fluids. We're not adding any wall rock to the magma because we're not assimilating. But if we were, this is where we would see the mass of the wall rock added to the magma. And column V would again be the cumulative tally of that anatectic melt as it's transferred from the wall rock subsystem to the magma subsystem. The next few columns starts with column W. And where it ends, honestly, just kind of depends on what your run is. So we call them the cyan columns, right? They start in W. That's always where your first mineral phase column would be. Depending on how many phases you crystallize out, you could have only 6 columns here, you could have 2 columns here, you could have 20 columns here. It really just depends on what's happened during your run. So these are the phases that occur, that crystallize out, and the masses of each phase that crystallize and fractionated out at each temperature step. So we can see for this run, spinel was on the liquidus. So here in row 6, that's our first fractionation step, and we've removed 0.009 grams of spinel. We keep removing spinel a few more temperature steps, and then we have this weird negative number. Basically, that's saying, oh, okay, well, spinel's no longer stable, so there was a little seed crystal here that things could nucleate on, but it's not necessary because spinel's not stable, so now we're going to subtract it. Again, it's so negligible. The mass is so negligible, it's in the thousandths place, and really what has happened during this step is that we add it in to nucleate, and then because nothing is nucleated, because spinel's not stable, we remove it. Because nothing is nucleated, all you see is the negative number. So I just wanted to let you know there's absolutely nothing to worry about there. Wendy Borson's done the math. If you have any questions regarding seed crystals, I highly advise you to contact her. The next column, column X, is again that running tally. How much spinel has been removed after each temperature decrement? What's the cumulative of the cumulates? Next, we have feldspar starting to show up after our second temperature step. And again, just so on and so forth. So here, our order of crystallization would be spinel in column W, feldspar in column Y. Then olivine shows up. Then we have clinopyroxene. We have one composition clinopyroxene at first, and then we get our second CPX composition coming in. We have another spinel structure mineral that's present immediately after our first recharge during that little isenthalpic step. But after that isenthalpic step, it's no longer stable. We've removed it, and so again, we have that negative number. After that, we have apatite starting to show up. And then we have hornblende, biotite, and then at the very end of our run, we have leucite. And so again, depending on your run parameters, you will have more or less phases. They will come in and out different times. Olivine might be on the liquidus in one run. Spinel might be on the liquidus in another. Clinopyroxene or feldspar might be in the liquidus in another simulation. It really, whatever happens in these columns is going to depend on the run that you've done. If we scroll over to the right, after the cyan columns, we have our blue columns. This is pretty much the same thing as the cyan columns, but it's for the recharge magma. And you'll notice that because it's only present in the orange rows. So at the first recharge event, the state of the magma is that it is at 800 degrees. We're adding 50 units in. It's partially crystalline. And these are the phases and masses of those crystals. So in that recharge, at the time of recharge, we have 3.02 grams of olivine, 4.7 grams of melolite, 11.43 grams of clinopyroxene, 6.69 grams of a second composition CPX, 9.84 grams of biotite, almost a gram of leucite, almost a gram of perovskite, and a little over a gram of apatite. And you can see that as we change the temperature conditions of our recharge, the compositions of our recharge, we can get different phases that show up. If I continue to scroll over, we have the green columns. And the green columns, again, those are our mineral phases and masses for the wall rock this time. So at 750 degrees, we have 138 grams of olivine, 280 grams of clinopyroxene, 470 grams of feldspar, and 14 grams of spinel, and then the other 10% of the wall rock is liquid. After this, we have our gray tabs, and this tells you the composition of the residual liquid in the magma subsystem. So of that liquid that's present in the magma, what is that liquid composition? So we're removing the cumulates, and then what's the new liquid composition? That's what's given here. And we have our standard major oxides. We do have ferrous and ferric iron divided up. If you haven't input some oxide, then of course, obviously, it won't be there. We also have the weight percent water and carbon dioxide present in the melt. After our gray columns, we have our white columns. This is the melt composition for our recharge magma. So at the time of recharge, we have some recharge magma. It's partially crystalline. We've already seen what the mineral phases and proportions are. Now, what's the liquid composition look like? Well, this is where it's given. Again, it's in major oxides. If you don't have some component input, it will come up as 0. And if we scroll to the right, we see the same thing for the wall rock. So in that one step in wall rock prime, the wall rock is 90% crystalline. We've seen the mineral phases and proportions, and this is what the composition of the liquid present in the wall rock looks like. So that's everything in the Run Summary tab. The next tab we have is our charts. So during our MCS run, if you'll remember, we had the Harker diagrams that you've preset, whatever you want on the X and Y axis, and they change if you manually refresh them during the run, so you can actually see how the composition of the residual liquid in the magma is evolving. Here, they just print them out so you can copy and paste them. You don't have to remake them. And what's really nice is it gives you your starting and your final temperature. So our simulation started with spinel in the liquidus at 1075 degrees. And it cooled. We had 3 recharge events, and our end temperature for this run was 848 degrees. The next tab is our solid formulas tab. This information tells you the composition of the phases present at each temperature step. It also tells you the compositions of the phases present during the wall rock prime operation. So if I go ahead and zoom in here, you can see that it's given in the mineral formula. So if I scroll down here we go. Our first temperature step, we have spinel on the liquidus. The temperature of the magma is at 1074.8 degrees. And then here we have the composition of that spinel. And I'll go ahead and zoom in just a little bit more so you guys can really see it. At the next temperature step, we have feldspar coming out in addition to spinel. So this is the composition of the spinel at the second temperature step. You can see it's pretty similar to the first spinel, but we've got a little bit less aluminum in it. Likewise, our feldspar composition is given here. So you could, if you wanted to calculate the weight percent composition for the different major oxide components in each mineral phase, you could calculate them from these formulas. However, if you'd like a quicker way to go about it, the melts.out files are still retained during an MCS run. So if I were to go back to my Finder, and I were to say go into this magma folder. In this magma folder, let me make it a little bit bigger so you guys can see it. I have my apatite.tbl file, and my feldspar.tbl file, and my melts.out file, and my hornblende.tbl file. So if you're like me and you actually like working with these melts out output files. They are retained here. After every run, though, just like with standalone melts, the files update and refresh. So it's important to make sure that you know exactly which run goes with which TBL file. I actually tend to empty these out and save them in an individual folder for each run. That way I have all of that information already handy. The final tab in our output file is chart data. So say you didn't exactly like the way that these charts looked because they look like Excel plots, which of course they are. In the chart data tab, we have all of the data populated already for you so that you can easily make your own graphs. So if I zoom in a little bit, here in column H, so for chart 1, this is the weight percent MgO in the magma. The next column is the weight percent SiO2 in the magma. And then the next column is the accompanying temperature for those two compositions. And you could effectively just highlight these and generate a new graph straight from this data. So this concludes our final tutorial on how to interpret output diagrams for the Magma Chamber Simulator. Hopefully you found these useful and you're getting ready to run your own simulations. As always, we here at the Magma Chamber Simulator are eager to help. If you have any questions, our contact information is available on our website. The link to the website will be put on this YouTube page shortly. And happy modeling!